Today I'm going to show you how to define a bi-directional imperfection on a structural element in SOFiSTiK. My name is George Schmidt and you can find me at SOFiSTiK, who is a leading supplier of software for analysis, design and detailing in the field of structural engineering and for whom I'm working as a consultant engineer. Today's episode is going to be super exciting, so let's get quickly start by creating a new project data. You can find it on you can see it on my screen. Created a new .py, saved it, and I'm going to input my model here in Teddy because the model is so simple. It's just a simple column, and I'm going to apply some imperfection in both directions on this column with a 100 kilonewton point load. Okay, so let's start with the material definition. I'm going to use module Aqua for that. Okay, and the title, let's say it will be material and cross section. Okay, the norm that I'm going to use is going to be the EN 1993-2005. I'm going to create a steel material with a number of 1, and the type is going to be a normal steel, and the classification of the steel is going to be 355. Okay, and now I need to create a cross section that I'm going to use for the beam elements. I also need to add a number. Then like type is going to be, let's say we are going to make an IPE section, IPE 600 for example, and an end. Okay, let's run it. Let's run this module and see what we are going to get. On my other screen it is running. Okay, and basically now if we go to the report browser, we can have a look at what we just created. We created the steel material and one cross section. Okay, yes, I can see my cross section here made of S355. Everything seems to be okay. Good. Okay. Now let's go back to the Teddy input and let's start with the system itself. So I'm going to create my system with the help of module SOFiMesh-C, and the title is going to be define structural elements, say. Okay. And then I'm going to do a system that is three-dimensional, that is going to be in the three-dimensional space. The group divisor is going to be 100, and the direction of the gravity is going to be the negative Z direction. Let's make two structural points at the beginning and at the end of my column. Structural point number 1 is going to be at x0, y0, and z0, and it's going to be fixed in against all deflection and against the rotation about the global z-axis. Let's create another structural point number 2, and the coordinate is going to be x0, y0, and z, say 12 meter, and the fixity at this point is going to be zp, so it's going to be supported in the global x and the global y direction, but not in the global z direction against deflections. Okay, and then let's create my structural line with a number of 1 between the points, sorry, number 1 and number 2 with a division of 12 times. So I'm going to create finally a beam element with a division of 12, and I'm going to assign this beam element into group number 1, and the cross section that I'm going to assign to this beam element is going to be number 1, which is the profile IP600. Okay, let's see how my system looks like. But I need to mesh my system, so I'm going to just add here control mesh 1, and then I can run it. Right mouse click and execute SOFiMesh C. It's running here, and if I'm looking at my system visualization, I will be able to see it on my other screen, of course, so I need to drag it here. This is my system, the IP section. Then I can see support conditions at the top and at the bottom. Everything looks like according to my wishes, according to my taste, so I can continue. And after the system, I'm going to just add the load that I want to apply at the very end of this example, which is going to be a 100 kilonewton point load. So I'm going to do that in module SOFI load. And the title could be definition of the loads. And I'm going to create load case number 1 without the specific type. And I'm just going to add a nodal load on node number 2. The type is a gravity type of loading with a value of 100 kilonewton. Okay, let's see and run the loading. And then let's see in WinGraph, for example, how this load looks like. Okay, for example, here I can see this. If I go to the loads and input loads, all loads, and I can see here very nicely that I have the 100 kilonewton on node number 2. Okay, good. I'm saving this picture. Okay, so now as I have my loading, I would like to define and make a first as a run with the self-weight. So I'm going to define the self-weight and run a linear analysis with it. I'm going to do that in module ASE. And the title could be analysis of self-weight. Good. And it's going to be a linear analysis. And I'm going to analyze a new load case 99 with the self-weight of 1. Okay, let's see if my structure is working for the self-weight or not. Okay, and now if I go to the system visualization, I have my load case 99 calculated. And yes, I can see that for the self-weight, the structure is really working without any warning or error, so everything seems to be fine. Okay, now I'm going to analyze the eigenvalues of my structure because I would like to use some of these eigenvalues to use for the imperfection analysis. So to create the imperfections from these eigenforms. So let's do it also with the module ASE or ASE. The title could be Assessment of the Buckling Eigenvalues. And let's say it's going to be also a linear analysis, and I'm going to use load case 99, so the self-weight load case as the primary load case, and I'm going to analyze the, let's say, first 10 eigenvalues, buckling eigenvalues, and I'm only interested about the positive eigenvalues. That's why I'm adding this lmin auto option. And I'm going to store the results in load case 101. Okay, let's run this and see how it works. Okay, let's go to the system visualization again. Okay, and here I can see my buckling vectors. This is my first buckling shape as I'm expecting. Everything seems to be okay. The second one, the third one, the fourth one, and the fifth one. Okay, I think I'm going to use for the imperfection the eigenform 101 and the eigenform 105. Okay, let's go back to the inputs and do so. And I'm again going to use the module ASE to do that. And the title here could be set the first eigenvalue as the first imperfection. Okay, so, and here comes the interesting part. So basically command obli is what we need to use here. And as I said, I would like to use the eigenform stored in load case 101. And I'm going to scale this eigenform to get the maximum deflection being equal with 0.1 meter. Okay, and I need to analyze some kind of a load case. So I'm just going to add load case 201, type none. So I'm not going to assign it to any action, and I'm going to add a dummy load, which is basically a fraction, a very small fraction of the self-weight, let's say 1 on the power of -4. Okay, let's run this and see the result. Okay, sorry. So if I go now to the system visualization, I can see that I have my load case 201 calculated. And if I freeze the image, it seems to be okay because I don't have any load in my system. The PZ is equal with 0. And really the imperfect shape is considered. So I am happy with the result. Really, the imperfection factorized by the load case 101 is considered in this analysis. So now what I need to do is do the same for the fifth eigenvalue form or the fifth eigenform. And I'm going to use again module ASE for that. And the title could be set the fifth eigenform as the second imperfection. And let's see. Again, I need to use the command obli, load case 105 that I want to factorize with the option Vmax. And let's say in this direction, I would like to achieve a 0.30 meter maximum deflection. And of course, I forgot something to I analyzed it in a linear manner, but now it is important in this case to analyze my structure according to the third order analysis, and I would like to use the PLC value from the load case 201. And I'm just going to create and analyze load case 202. Again, we type none with, again, a dummy load, which is also the self-weight factorized with a very small value. And now I must copy in the first load case, which contains the 100 kilonewton nodal load. Okay, so again, what I did here in the very last other run is set the imperfection from the eigenform 105, factorized it to get the maximum deflection being equal with 0.3 meter. And then I run a third order analysis considering load case 201 as the primary load case. So the stresses and the deflections is going to be considered in this analysis here. And I'm going to run load case 202 with a dummy load. But on the other hand, I'm going to copy in load case 1 as the nodal load with a value of 100 kilonewton. Let's see the result. Okay, and now I have it. And really, the only load that I'm having in the system is the 100 kilonewton. Is the 100 kilonewton nodal load. And if I go, for example, to the top view and make the amplitude of the deformation a little bit bigger, I can really see that the deflection is not just occurring in the in the global x direction, but a little bit also in the global y direction. And this is what I was anticipating. And now if I go to the wind graph, I can also check my results. So first of all, I can check the loads in the system in load case 201, which is really the 100 kilonewton itself. And if I go to the results and node and nodal displacements, and for example, I'm going to represent the vector of the displacements, I can see that it is an arbitrary direction, so between x and y axis, and the value of it is 327 millimeter, as we can see. So this is how you can basically consider imperfections based on the buckling eigenforms in one or more direction. Okay, that was it. Got it good. And that was it for today. Thank you so much for hanging out with me, and I had a great time creating this tutorial, and I hope you enjoyed watching it. Thanks and bye.